So, last time we discussed uniformly magnetized material, and we took this example of disc, and then from that we showed that if you have a kind of disc, then and it is uniformly magnetized, then on the periphery of that disc you have a current, and that current is known as bound surface current, right, bound surface current, and it is related to the magnetization. If the magnetization is m, then the surface current density is also, it has the same magnitude, and that is m, and the direction is of course given by this m cross n cap. So, this was an example, the disc was an example, but of any shape, material of any shape, if it is uniformly magnetized, then on the surface of that material you will have this kind of bound current, and given by the same equation m cross n. So, whatever is the surface, suppose this is the surface, suppose this is the surface, suppose this is the material, and suppose this is uniformly magnetized, right. Suppose the magnetization is like this and uniform everywhere in the volume. Then if you are here, you can ask what is the magnetization. So, this is the magnetization. What is the normal, unit normal at this surface here. So, this is the direction, unit vector in this direction. This m, this n cap, when you do m vector cross n cap vector, you get the surface current here, direction and magnitude, and similarly here, similarly here, similarly here, similarly everywhere. So, whatever is the size, shape of the material, if it is uniformly magnetized, then on the surface of that material you may expect a surface bound current density, and that flows along the surface, and the magnitude is given by that m cross n. So, this was about uniform magnetization. Most of our bar magnets which we use are supposedly, and they are, to a very good approximation, they are uniformly magnetized. That is why you take some pins and then get them close to this end of the magnet or that end of the magnet. Normally equal number of pins will be attracted at the ends, showing that okay, the strength is same. But if you put the pins in the middle region somewhere, then they do not attract, right. So, often in schools we hear that the magnet is strongest near the ends and weak near the middle, but that is not the case. It is uniformly magnetized. And then why it attracts only at the ends, not at the middle. So, it is very simple to understand that if you have this say cylindrical magnet, the cross section normally is not round, it is rectangular, but does not matter, whatever is the shape, the basic physics remains the same. So, if this is the magnet, and then uniformly magnetized in this direction, everywhere the magnetization is this m. We have magnetized it. That means all those atomic dipole moments which were there, we tried to align, or if there are domains, the domains are in this direction, the magnetic moment of the domains are preferably or in this direction. So, you have a uniform magnetization in this z direction. But then the current comes from this bound current, this magnetic field comes from this bound current, right. All these things you then correspondingly write the bound currents, and the bound currents will be like this everywhere, anywhere the bound currents will be like this, will be like this. So, on the surface everywhere you have this current. So, it is like a solenoid. That is why we say that a bar magnet, a permanent magnet is like a solenoid. It is not like solenoid, it is solenoid, because you do have these bound currents on the surface and going in that phi cap direction. So, this is the structure to get the magnetic field of this magnet anywhere, inside, outside, anywhere, here. You just have to see this current. And from this current you calculate the magnetic field using Biot-Savart law or Ampere's law or vector potential, whatever method it suits you, use that and you can find the magnetic field. So, here it is a solenoid, this is the same structure. In solenoid also goes like this. So, in solenoid you say that n, small n, is the number of turns per unit length, and each turn carries a current I. So, in length L you will have n into L turns and then I, this much current. So, if you take a length L, how much current is crossing here? That is given by this. And in this case, if the current density is K, which is in magnitude equal to M, then you can ask how much is this bound current going. So, that bound current going will be this K times L, and therefore, you will have exactly the same structure, right. So, you have Ni per unit length, Ni is the current per unit length. Right. In L length, this much current is going. Here, this K is the current per unit length. You take a length L and K times L, that much current is crossing here. So, just in place of Ni, you write K and you get this magnetic field, whatever you want. Okay. That Ni is to be replaced by K, and then the solenoid field is same as this magnet field. That is how it works. Now what happens in a solenoid? You have a finite solenoid. Because your bar magnet has to be finite, and what kind of magnetic field is there? So, you remember that we had done it when we were doing this solenoid, that if you have a finite solenoid, then the field lines are like this. Maybe you can start somewhere from here, and one line can go like this, and then this line continues on the other side, and then it closes. Magnetic field lines are always closed lines, and similarly you will have a magnetic field like this, which will go and come back somewhere of this type. Similarly, you will have another line which is, say, close to the center, then it will go further, and then it will come back from a large distance, and so on, and the same this side, like this. Now, here one thing is that as compared to outside the solenoid, just outside, and then just end. If you compare this magnetic field is quite strong as compared to this. If it is a very long solenoid, then the outside field is 0 and inside field is mu naught Ni parallel. But once it reaches the end, it has to diverge and then close. These are all closed lines. So, here if you see, the magnetic field is small, and here the magnetic field is large, but more than that, remember, if you have a pin or a small thing and you place it in a uniform magnetic field, however strong, very strong magnetic field, but uniform, and then I place my material here. This is, say, just an alpine or some iron nail or something. So, this magnetic field will magnetize this iron nail, and if this whole thing is uniform, if this magnetic field is all uniform, then hopefully this nail will also get uniform magnetization, and then the magnetic field will not exert any force on this nail, however strong the field be, right? Because if you have a dipole, you know, the net force on the dipole, net magnetic force on the dipole is 0 if the magnetic field is uniform. So, variation in magnetic field is important, or in our that magnetic charge model, I can say that, oh, all right, here it is minus qm and here it is plus qm, and if the field is same, then the two forces are same in magnitude, opposite in direction. So, variation is needed, and here is the variation, and here is the variation. So, if you bring a pin here or nail here, it will be attracted, but if you place it here, you will find that almost no force is there, right. So, but inside the magnet, if you go inside the magnet, the field is strongest here and it becomes weak here. So, that is the kind of thing. Now, the end from where the field lines are coming out, this end is known as north pole, people call it north pole, and the other end where the field lines are entering, that is known as south pole. And people talk of similar poles and dissimilar poles, attract, repel, etc., etc. Now, you know that there is nothing like poles. Your magnet is here, your magnet is here, your currents are this. So, this current here, last, this loop here, this loop here, this loop here, and this loop here, they are all identical, they are all identical. If it is anticlockwise here, it is anticlockwise here. If it is clockwise here, it is clockwise here. Not only the two ends, even the middle. This current loop is also same as this current loop. So, there is nothing special here which you call south pole, or nothing special here which you call north pole. It is all anticlockwise or clockwise currents, identical structure, only shifted. Only shifted. The loop is here, you shift it, you will get this loop, you shift it, you get this loop. No change, no material change, is the same loop. But then how do we say that the two north poles, if they are coming close to each other, then they will repel, and if south pole comes there, then it attracts, as if in electrostatics we do say that, yes, the positive charge and the negative charge are two different entities, and then positive charges repel, negative charges repel, positive negative charges attract. But here they are not two different entities, you do not have two kinds. In electric case, yes, you have two kinds of these charges, but which create this magnetic field, but this electric field, but here these are the current loops, and the current loops are all identical here to here. Magnetization all identical, the magnetization here, the magnetization here, the magnetization here, the magnetization here, magnetization here, everything here and here and here and here are identical, but still it appears as if there are two kinds of poles, and similar poles repel and dissimilar poles attract. So, we can understand it that attraction repulsion on the basis of what we have discussed, and let me take our magnets like this. Suppose this is a material, this is a magnetized material, the magnetization is in the z direction, and if the magnetization is z direction, the surface current will be in phi cap direction. So, the currents will be like this. I am just trying to draw the current. So, here the current will be like this, here the current will be like this. Can you see the arrow? This arrow here and this arrow here. So, the current is like this, m cross n cap, essentially m cross n cap. The current is like this and so on. You can do it. You can do it for the entire mango, and let me quickly do it here and then come here near the end, all right. So, if this is the current, the magnetic field will be, the field lines will come from this side. So, this is that so called north pole, this is the so called north pole, and this is the so called south pole. Let me take another magnet and we do the same thing here, same identical magnet, identically magnetized. So, the currents will be like this. This is the arrow, this is the arrow, this is the arrow. This is the arrow, and this is that arrow at the last one, and the magnetic field is coming here and going here. So, this people will say that this is north pole, this is north pole, and this is south pole. Okay. Now, let me bring these two magnets which are identical. You can see that, you can see that it is all identical, north pole here, north pole here, the arrows are like that, similar arrows on the two magnets, and suppose I put it here, I put it here. So, here is that N, north pole of this, and here is the S. But think in terms of currents. What are the currents? On this mango, this is the current is going like this, see the arrow, it is going like this, on this it is going like this. The currents are parallel, the currents are parallel, and you know that parallel currents attract, therefore, it is attracting. It is not there are dissimilar poles, something different kind of thing here and different kind of thing here, they are dissimilar, they are not dissimilar, they are similar, and similar in the sense here you have current and identically same current is here, same current, same direction, and therefore, this current and this current, they are parallel to each other, and parallel currents attract. That is why this N and this S, they attract. If I put it here, if I put it here, the same story. If I put it here, the same story once again. This current and this current are same, this current going this way, this current going this way. So, parallel currents will attract anyway. Here also, see this is also that same in the same direction, this one. So, this one is also attracting this. Not only this is attracting this is also attracting this, because here also you have parallel currents. So, not only that north is attracting south, the south is also attracting south. Okay. So, there is an overall attraction, but if I invert one of them, see what happens now, right. So, it was like this and I have inverted this. So, this N goes here and S goes here, this N is here and this S is here. Now, look at the arrows, here the current is going like this and here the current is going like this, here the current is going like this and here the current is going like this. They are anti-parallel currents. the current wise, this current is this way, this current is this way, they are dissimilar currents, they are anti-parallel currents, and because of this dissimilarity, because of this anti-parallel, these are repelling each other. So, not the similar ones are repelling, the dissimilar ones are repelling. And remember, here also, this end also, the current is this way on this magnet and current is this way on this magnet. It is being repelled by not only this current, but also by this current. But overall, when you just look at it from outside, you say that okay, fine, this is N, this is N, and therefore they are repelling. And if I have inverted it here, you will say that okay, you have brought S here, N here, and therefore they are attracting. So, this mechanism of attraction repulsion is very interesting of magnets, and if you understand that, then you will enjoy more. So, this is when we talked about the uniform magnetization, and as I mentioned last time, if the magnetization is not uniform, then in the interior also you can have bound currents, and let's talk more on that. We consider that same disk structure. Suppose I have a disk here, and then the disk has some thickness. Remember our atta, and we have our axis system, y axis, z axis is vertical, and this plane is the xy plane. So, this is x directions, parallel to the x direction we drew some lines, parallel to the y directions we drew some lines, and then we took such blocks, and then depth dz, that is the thickness, and this is your dy, this is your dx, and depth. So, one block is like this, and similarly this block here is like this, and so on. Now, this block and this block, consider these two blocks, and I am only drawing this part. Okay, this block, and of course the depth is there, and this is our dy, this is our dy, and this is our dx, and we have depth dz, okay, like this. Now, here suppose your magnetization is in k cap direction, in z cap direction, right. There is xy plane and there is some small thickness, and the magnetization is up. So, it is like this, but this m is a function of y, it is not constant, it is not uniform. So, here the m is different magnitude, here m is different in magnitude, right. So, corresponding current, the corresponding current will be like this, the corresponding current will be like this here, and for this block the corresponding current at the surface of that block will be like this. And how much is this? How much is the current? That remember how did we calculate? If this is magnetization M considered uniform in this part, that is how we do it in calculus. So, the total dipole moment will be magnetic dipole moment of the left block will be the magnetization and times the volume dx dy dz. That is how the magnetization is defined. You take a volume and see how much is the magnetic dipole moment, divide by that, and that gives you m. So, m times the volume element will give you the dipole moment. And if this is I, if this current is I, the area of the loop is dx dy. The area of the loop is dx dy. So, if I have a current I here, then the dipole moment of that will be I times and this dx dy. And I have to make these two equal, so that this this whole magnetized block can be replaced by corresponding current loop for further calculations, etc. So, what is this then? I should be equal to my and dz. This is I. Now, this is I, this is I. So, this current here is m at y. Let me say it, m at y. Yeah, this is m at y. So, this is m at y and then dz. Dz is the thickness, this is dz. Okay, and this my we are taking at the center, and then for this dy distance we consider it uniform. That is how we do it on all kinds of differential equations, differential calculus and integral calculus. But for this loop, m is here, which is m at y plus dy, right? Center to center distance is again this dy. So, m at dy dz, y plus dy, and then multiplied by dz, that is the current, and that current is in this direction. That current is in this direction. That is your x direction, right? This is y, this is z, and this is x direction. So, it is that. Hence, the current here, net current, the two currents taken together, that current will be equal to m at y plus dy dz and minus m at y and dz. So, this is the current which is going in x direction. This is the current which is going in x direction, right. Now, this we can write as this m at y plus dy will be m at y plus rate of change of m with respect to y, and then how much y has changed dy. Okay. Taylor's expansion, the first two terms, m at y and plus the rate of change of y is delta m delta y, and then how much is the we have gone in that direction dy. So, this is the rate of change and this is how much we have gone. So, this is the change. So, my plus this and minus my times dz, and this is delta m and delta y here and dy and dz and this dz, so dz. And m is in, we have taken, simple case, m we have taken in the direction of k. So, I can also write this as del mz, this is the z component dy dz. Of course, there is no x component, there is no y component. So, the whole magnitude is same as the z component, but let us write it this way. So, that is equal to the current, and this current is going in x direction. This current is going in x direction. What is the volume current density? Now, it is volume, it is not on the surface, it is in the interior, and the entire volume will have the current. So, volume current density J, which is I divided by the area. If it is going in x direction, you take an area perpendicular to that small area. So, perpendicular to x direction will be dy dz. So, that dy dz is here, and then see how much current is going, divide by that area, j by a, I by a. So, that is equal to del mz del y. This is our j, and it is in x direction. So, I can put a vector here and I cap here, right. The current which we have deduced from here, that is in x direction. This is our x direction, in fact, this is our x direction. So, it is in this way. Now, if you calculate what is curl of m, what is curl of M? Calculate this. This is I cap here, j cap here, k cap here, del x here, del y here, and del z here. And then for our case, M is in k cap direction. So we would write mx, my, mz. So it will be 0, 0, and then this mz. And hence it will be I cap, this and this. So del mz del y, and then minus this and this, which is 0, j cap, you omit these two mentally. So del x of mz. In x direction we are not assuming variation. We have, in our simple case, we have assumed it in y direction. So this is 0, this is anyway 0, so it is 0, and k cap is 0. If you take this k cap, then del x of 0 minus del y of 0. So this is I cap and del mz del y. So what you see is that curl of M at same as this J, current density, volume current density. We write it JB, remember bound. This B is for bound. This is bound current. And what do I mean by bound? This interior current also. This interior current is also not because electrons which can go over large distances. All electrons are still bound to their nuclei, and still they are giving this kind of current. So this is called bound current. It's volume bound current. Okay, it's volume bound current. This is equal to curl of M. This is equal to curl of M. This we derived for a very simple situation where we said that okay, our magnetization is in k direction, in z direction, and it varies only in y direction. But then you can generalize, the mathematics will be slightly more complicated, but this is the result. This is the result. So we are through. We are through. We know how much is the current on the surface and how much is the current in the interior. Most of the time we are concerned with uniform magnetization, most of the time, and therefore we do not need it quite often. But yes, this is the structure. Any kind of magnetization, magnetized material can be thought of a combination of a volume current and a surface current. And then if you want magnetic field because of this magnetized material, you only find the magnetic field because of this current and because of this current, and that is how you get it. So with this much we will stop today, and next day I will introduce a new vector field which is very interesting, H. It is called H magnetic field, H field, okay, H field. It is called H field. So we will introduce this field